With a basic understanding of how the memory works, we can start to talk about how a machine language program runs directly on the computer's microprocessor. First, the use of permanent memory is generally governed by a file system, like NTFS for Windows or APFS for Mac. The file system bundles addresses of content in the permanent memory into structures called files. The file system tracks the types of these files, with a major distinction between file types being the executable files that contain machine language programs, or the data files that are created and manipulated using these programs. Remember that the permanent memory is relatively slow, so the first step to executing a program is to copy the machine language to the RAM to maximize the speed at which it can run on the processor. Let's say the program you are running is something like a text editor for editing code or a word processor for editing a document. In these cases, you are probably opening a data file soon after starting the program, if not opening that data file at the same time you are starting the program. Either way, the data file you're opening is also likely to be copied to RAM for quick access and manipulation, unless the data file is so large that it cannot fit in RAM all at once. In these cases, the programs have to know how to deal with the data file a little at a time and periodically write the bits you are not changing back to permanent memory to clear space in RAM for the parts you are changing. With copies of the program and data in the rapidly accessible RAM, let's look in a bit more detail at how the processor carries out operations on the data. First, the processor has small and extremely high-speed memory locations called registers. A given operation might be based on copying information from the memory to the input and instruction registers, and then copying the results from the output register back to memory. The input register is likely to receive information from RAM that was a copy of the input file. The information copied to the input register is likely important for ultimately changing or adding to the content of that data file. Then, a given instruction from the machine language program is copied to the instruction register. With the bits of the input and instruction registers at their appropriate values to perform that instruction, the logic circuitry in the processor produces the bits of the results of that instruction in the output register. Those results are copied back into the RAM, either in the process of changing the value of an existing data structure or creating a new one as defined by the operations on variables in the original program. One of these cycles is only changing 64 bits or 8 bytes of data at a time, so the execution of a large number of instructions may be necessary to accomplish a single line of code in a lower level compiled language like C or Fortran. Even more instructions are likely necessary for accomplishing a single line of code in a higher level scripting language like R or Python. This may seem horribly inefficient, and you may be wondering how the computer handles data files that are on the order of megabytes in size when it's dealing with only 8 bytes at a time. If you check the specs on processors at the time of this video, you will see that their clock speed is likely on the order of gigahertz. This means that these operations are happening on the order of billions of times a second. Also, processors at the time of this video are likely to have at least 4 independent cores with their own sets of registers running a program on a separate thread, meaning that they can perform at least 4 instructions for different programs at effectively the same time. Perhaps after performing a few trillion or quadrillion instructions, it may be time to copy data from RAM back to the permanent memory. For example, you have done some work on your R code in a text editor, and it is saved when you execute the R program to test it. Or maybe you are done editing a document in a word processor and you are saving it so you can submit it for an assignment. These are just a couple of examples of when the data structures in RAM need to be translated back into the appropriate format for the associated data file in permanent memory. While myriads of other types of operations are necessary for a computer to operate, not the least of which are interactions with the interfaces, this should give you enough information about how a microprocessor works to understand the implications on how we write programs. First, the operation of RAM is critical to how we think about data typing when writing programs. And second, the nature of how many individual machine language instructions are needed to execute a single line of code suggests why customized machine language compiled from lower level languages like C and Fortran tend to be faster than the same functions running on a precompiled interpreter for scripting languages like R or Python.